Welcome back to the hyperbolic suffering chamber. It is a chamber where suffering happens at the rate 5x of the normal world. So if you think working is bad, if you think, you're coming home from work and you drop the keys before you put it into the lock, if you think that's bad, the hyperbolic suffering chamber is a chamber designed to multiply that suffering by a rate or a factor of 5. So pretty exciting chamber if you ask me, but not more exciting than the YouTube comments that we have from our fellow algorithms. We have a comment from the God King, the legend, and the man himself, Thomas Wong Coding. Haven't checked in for a while, bro. Congrats on oh yeah, true. 1K, so that's a big milestone. Got to keep grinding. Thank you, God King. Feel strong, man. Also, cool. What is TV in the highest? Oh, I didn't know they had these badges. Feel strong, man. Yeah, Thomas is a legend, man. Hey, Manny, do link the problem you're solving in the description as well. We can get consistent with you. Oh, wait, true. Wait, actually 5 head. Actually 5 head comment. Will do this going forward. That's actually genius. Yeah, I'll start doing that. Hello, Manny. Found your channel recently. It's kind of cool seeing you. Happy with your LeetCode progress. True. Actually, we are less than happy. We are upset. Our progress, unacceptable. Nah, I'm joking. I obviously wish for more progress, but it do be like that, which is unfortunate. You mentioned early on reading about algorithm textbooks. Have any recommendations that help the most? Algorithm CLRS is the best one. I haven't tried that one, but I've heard good things. I think people mostly pass around the same names. I am reading ADM and I like it, but heard good things about CLRS and elements of programming too. Yeah, it's interesting. I think just as long as you do some supplementary reading, it'll help. I'm not, obviously I'm not in the leagues of the God Kings, the international grandmasters yet, but I have the Conqueror's hockey, so we should be able to get there soon. But yeah, I think just reading the ADM just helped me have a name to be able to categorize problems. And I think that one of the things they say in the book, it's less about knowing. I mean, I personally think this is not true. Actually, I'll say the part instead. Something that really helps is knowing the problem spaces. So there's just a lot of problems that have been solved already, like longest path and other stuff, that once you know the problem, like transitive closure and all that stuff, apparently, and I think this is true, it's easier to, box it into some constraints and solve it. But I have no idea what transitive closure means. But there are other problems I'm aware of now, like all pairs, shortest path, and stuff like that. Death to the lead. Yeah, the LeetCode elite. The LeetCode elite must be stopped. This is true. This is actually true. The LeetCode elite have spent too much time up in their ivory towers and their massive castles and their thousands of problems solved. It's time to shake the landscape. We, the LeetCode peasants, must stop them. And that is the main goal of the hyperbolic coding chamber. I'm also doing LeetCode every day for a month through hard work. Hey, keep going, brother. We will be rewarded with more than riches. We will be rewarded with focus. Also, personal achievement. Also, going further than one believed one could. She saw... I'm pretty sure Island Eagles posted this to troll me. She saw seashells on the seashore. However, my pronouncing prowess cannot be stopped. And so I look forward to the next challenge. But you know what I'm not looking forward to? A problem called ones and zeros. So this problem has been torturing me, but it's actually, I forgot to do something before we started. I do like a warm-up set before I get started. I forgot to do. Yeah, I'll have to fix that over the weekend, but that is unfortunate. But Yeah, so yeah. Um yeah, this problem has been tormenting me, and we're actually a little bit short on time today. I think Fridays are just going to be like this, a little bit short on time. So I'm thinking we're going to hit the 30-minute bongo button. That should put us at, no, I think we can squeeze in 40 minutes. I think we can. But that's what we're going to aim for. I think we're getting so much closer. We're getting so much closer. Basically, it's a DP problem. We're trying to formulate it as a DAG so we can run a shortest path algorithm on it, which is a modification to get the longest path. However, I thought this was simpler than it was, and it's not. So I think there are two axes for improvement here that could lead us to solving the problem today, but I'm skeptical. But we shall see. So one improvement, I'm going to keep it a $1,000. I'm doing anything right now. This solution for this problem is almost 135 lines of code. Something is clearly wrong, right? We had a function called get zeros and ones, which honestly is not that great of a function. And we should have just cached the zeros and ones for a string, which would dramatically reduce the, maybe not dramatically, but it would give us some improvement. And then we started running Dijkstra's, which is an n squared algorithm n times for n cubed, which on paper sounds fine, but the actual runtime is probably worse than n squared because of all the nonsense we're doing in here. So we need to go back to when things were simpler. So I'm going to remove this n cubed version, and I think we can solve this by just running Dijkstra's once. And what it should return is 3 arrays, parent, distance, and yeah, just parent and distance. Yeah, just parent and distance, and entry will be for debugging. And we'll just say equals Dijkstra's, will pass in stirs, m, n, and we actually don't need the starting vertex anymore because we're going to change a couple of things. We had a function called getPath, which, to be honest, was doing anything. But it might still be reusable. Here, we tried to figure out the path to take through the array, the parent array, but it ended up kind of being anything. Yeah, this is just anything. And so instead we're just going to return parent and distance. And entry, and then we'll handle the output after. Which is going to change the output of the function from number to 2 arrays of type number. And then from here, oh, wait. No, wait. Wait, why is this giving me, oh no, I forgot. We're returning 3 items. Okay. This is being very ghetto. I should fix that. Calculate is a mess as well. I think we should be satisfied now. And then, God, I'm just editing code. It hasn't even started yet. This is taking too long. Then I'll print parent. Yeah, and max was returning anything. V is gone. V is just going to equal to start. V is going to be equal to 0 to start. And the way that we're currently going about this, the edges that you can choose from, we need to actually make this a DAG. But we're doing anything right now. To make this a DAG that makes sense and to rephrase this DP problem as a problem for which we can actually find the shortest path to, there are two axes for improvement. Two axes for improvement. The first axis would be the longest path Dijkstra's generates the shortest path between S and all other vertices. But in our current implementation, our graph is just represented by the numbers in the array, or the binary strings in the array. What would be better would be something we did before in another problem where we used Dijkstra's, was to create an artificial end, right? But it never occurred to me that we could create an artificial start. So two axes for improvement would be create an artificial S vertex and artificial E vertex. Then we can phrase the problem as Dijkstra's, right? Starting from the source vertex S. If we start from the source vertex S, then we'll find the shortest path between S and all the vertices, including E, which is our end vertex. And then from there, we can swap shortest path to longest path. The other thing phrase as shortest path from S to E. And I'll zoom. Two, we need an actual DAG. We actually need a directed acyclic graph. We're doing anything. We've been doing anything, bro. The way we have our edges as a potential, we filter through all the indexes. Now, the real question, right, is given input like we have here, right? The question is, the hard question is, right, how do we create the DAG? How do we create the DAG, right? So we'd like there to be some ordering, but the ordering has to make sense with respect to the problem. So one thing we could do is figure out if a longer string is better or worse for longest path. If we wanted the longest path, ideally we want the shortest string. This would work ideally for us because now this 1, 1 here would not be able to travel to these strings because they would not make it. They would make the path shorter rather than longer. So what if you only have an edge What if you only have an edge? Only have an edge if and only if the vertex is less than, if the string is less than or equal, if the string is less than or equal, only have an edge if and only if the string is less than or equal to your if the candidate string is less than or equal to candidate string length equal to current string length. You only have an edge if and only if the candidate string length is less than or equal to the string length. So 9 here would not have an edge to any of these numbers here. But, and we should just remove this nonsense up top, vertex 0 would not have an edge to vertex 1. But all 3 of these vertexes would have an edge to 1. The other thing is that we'll also do it based on DFS. Well, let's see if we need that. Can we use a, can this create, well yeah, if we said less than or equal, then these would also have edges to each other. These would also have edges to each other. I think one thing we can do first to actually make some progress is do the first one. So we can add the artificial vertex S and E. Actually, let me see what I'm getting right now for distance and parent. All right, it's kind of hard to make sense of this because the start vertex is the first vertex. So we'll just add 2 elements to the string dot length, and what we'll say is set up S and E. And what we'll say is distance sub 0 is equal to 0, and distance sub distance dot length minus 1 is also equal to 0. So the wait to get to S and E shouldn't add anything to the distance. And then V equal to 0, we can remove distance of V equals 0. And so we pretty much want an edge to exist, outgoing edge to exist from S to every vertex except E, and then an outgoing vertex to exist from F for every vertex except start and end to end. So the edges are going to be a little bit implicit here, while they just are. And now I'm thinking we could just build the edges normally, in the sense that this would be a lot less confusing of edges sub V if it worked more like this. So what we're going to do is, instead, we had edges here, and we're just going to switch to like a regular implementation of the edges here. So we're going to have edges, which is really just going to be a map of number to an array of tuples where we have the weight and the vertex, and this is just going to be an array equals new map and then here we can just say here we'll just have to create the edges, right? So we actually need an actual DAG. But one of the things we can set up is that edges sub 0, we can do edges dot set 0, right? That start vertex. Right now we're going to set it to pretty much an array of tuples. We pretty much can do distance dot map. We don't really need the distance, we really just need the index. Then we'll turn it to Then we'll have distance is a map. I think I'm trying to do this functionally for no reason. You can literally just do, what I'm trying to literally do is just pretty much go from let I equals 1, I is less than distance dot length minus 1, because we don't want an edge from start to end, I plus plus. So we give us these, and I pretty much just want to say equal to an array, right? And then I'll just say start edges dot push. We're just going to push on a tuple I, which is the vertex, and then the actual weight of the vertex, or the vertex you actually end up at, would be I, and the second one is going to be the weight. To get that, we can just do stirs sub I dot length. This would give them all an out. S would have an outgoing edge to all vertices. At the end, I could say edges dot set 0 start edges, or S edges. This is really what it is. And then for S edges, we also need the end edges. And I know it's kind of ghetto that I'm duplicating all this code. We're going to say E edges. And then pretty much I equals 1. Actually, I think we can make them together. Then we'd have E edges, except the weight of the edge to get to end was nothing. And I'm just going to say console.log edges. There's a lot of W just be equal to, oh, I think what they're wanting me to do is just swap this is W, right? And then we have weight. S edges dot push. think we should have to do I minus 1. Edges of V is not iterable? It should be, though. Oh, right. We don't have the other ones. Right. So let me see if these edges make sense. So you have a path to vertex 1, length 2. We should have 2, 4, 6, 1, 1. 1, 1, and they all have a path to end, which is 0. That makes sense. Now we just need the ones in between. Need the edges for the in-between. Now you only have, and then we can comment out this. I guess now here's the last missing piece, the edges in between. The edges in between. Now the edges in between we wrote something down, only have an edge if the candidate string length is less than or equal to the current string length, which is not exactly perfect. You know, and we'll say, and not visited. If that's the case, right, we would have, let me upgrade all of these, right, because 0 would be start. So 1, 1, 1, 0, 0, 1. Do we have an edge from 1 to any other node? No, right? We don't. So we start with S up here, right? With S up there, then we'd look at the path, the cost for all of these. We have 3, 4, 4, and 4, right? Then we take pretty much the first longest path, which would be 2 here, while setting the distance to this one to be 3. Actually, let me figure out the graph first if we run. So would there be a path to this one? No. There would be a path from 2 to 3, then 3 to 4. Two to 3, 3 to 4, 2 to 3, 3 to 4. So you'd only have an edge if the candidate string length is less than or equal, and we haven't seen it yet. So we wouldn't have seen 1, but its length isn't correct, so we wouldn't have an edge to it. And we have seen 2 already, so it can't be an edge. And our self can't be an edge, so we can only have an outgoing edge from 3 to 4. So here we just need to pretty much generate all the edges. So we'd start at let I equals 1. I is less than distance dot length minus 1, I plus plus, which is the edge. Then we'd have to duplicate it. Oh, no. Then we'd say edges dot set the edges for this to be R. And I guess we could just say vertex. Actually, we'll just say neighbors, which is going to be an array of tuples. So we'll set it equal to neighbors, right? And to get neighbors, pretty much we just want an array of 0 to the code here is written so bad. We're just going to call this real vertexes, which literally makes no sense. We're just going to say I is equal to 1. I is equal to 0. I just want a thing that says 0 to n. I guess we can just map over distance. So we'll just do that. We'll do distance dot map we don't care about the value, we just want the index. Right there. Now here we want to filter out some of these indexes. Now you want to filter them out. Filtered it out, right? Index does not equal 0, and index does not equal distance dot length minus 1. I just want to see if we're at least getting an undirected. Okay, so we are. That is perfect. Right, and what else do we want to filter out? Your current length would be equal to strs sub I dot length but minus 1. And so we want to say filter out if you're greater than it. So if we don't want an edge to have we don't want a vertex to have an edge to anything that has, what did I write? Only have an edge if the candidate string is less than or equal to the current string length. Yeah, so if it's greater than it, we want to filter it out. So let's see, based on the input string. So vertex 1 would have an edge to 4 and 5, right? Because it's less than it, right? 4 and 5. Vertex 2 has an edge to 1 and 4 and 5. Vertex 3 has an edge to 1, 2, 4 and 5, and 4 and 5 don't have an edge anywhere. Actually, a small issue because they all should have an edge to end. I'm not following what the problem is. I just took out. Index is not equal 0, and index, I'm just taking out this case here. What's the problem with removing that case? And index is not equal distance dot length. I see. So I think I just have to add neighbors dot push. All right, so they can all reach, now they can all reach the end with a weight of 0. Except the end. So now we just need to make them tuple. The code on this is literally spaghetti code. This is bad, but it is what it is. We're gonna say index, and then what you get here is actually stirs sub index -1 dot length. And then instead of edges sub v, we'll just say edges dot get. I don't think we need the whole zeros and ones thing anymore. Oh yeah, I'm missing one thing, but I want to see what we get as output. And there's one more issue, and that issue is that it's not acyclic. And so the final thing is that you can't visit an edge we've already visited before. Well, likes just can't do that. Shortest path. I don't think we need entries. It's making it a little confusing. We can keep distance. I think I'm realizing now I messed up when creating the E part. I meant to say that start has an edge to every vertex, and all the individual vertexes except for start and end should have a vertex to end. Instead, what I have is end has a vertex, end has an edge to every vertex, which is not, doesn't really make any sense. In theory, 5 should just be an empty array. So this should just be empty. All right, every node has now a vertex to 6, and 6 is the end. Expected. True. I have to go, but I feel like I'm not done on this problem. I just need a longer stretch of time with it. Yeah, I have to go, rip. But we'll be back tomorrow. I think we're getting close though. The S to E, I just need to marinate on it more.